Hold on a second. We are Oxford. Hello, we will be starting in Hello, we will be starting in 5 minutes. Let's wait 5 minutes for people to join. Then we will start the class. Hello everyone, I am Swastik Chakraborty, a research scholar in IIT Kharagpur. So I am a member of the I am a member of the team for the course Analog Communications instructed by Professor Gautam Dash. So I will be conducting live problem solving sessions where I will be solving few problems related to the material that have been taught in the week preceding to the live session. So for this class we will be tackling the problems that are related to what is taught in week 1. So this will be a live problem solving session. So we will be solving these problems, and at the same time you can come up with any doubt regarding the problems or regarding whatever has been taught till now in the class. So this take this also as a doubt clearing session. So any and all doubts are welcome. At any time you can interrupt me and press your doubts, ask your doubts. I will be happy to answer them. Okay, so with that in mind, we will proceed with our assignments. I will be sharing the screen. Just tell me, one of you just tell me whether I am audible and my screen is visible or not. Okay. Okay, fine. So let's start with week one's problems. So week one's lectures are lecture 1 to 7, and they mainly correspond with to the Fourier series, Fourier transform. Fourier series rather, not even transform, Fourier series. They are related to Fourier series. So I hope you have gone through the lectures for I have got lecture 1 to 7, and if you have any doubts, as I said, you can interrupt me anytime. So question 1 is, the power of an energy signal is always 0. So I will first be hiding the answer. So power of an energy signal is always 0. Is it true or is it false? Okay, class, start giving your answers. Like, what do you think? Is it true or is it false? Power of an energy signal is always 0. What do you think? Hello, please respond. Okay, you may unmute the mic and you unmute the mic and say the answer. This is an interactive session. Okay, so yes, the answer is true. True is the correct answer. The power of an energy signal is always 0. Now we will go as to why. So what do you mean by an energy signal? Energy signal means a signal whose integration of modulus square converges. If this converges to a finite quantity, then xt is an energy signal. What is a power signal? Power signal is also known as a periodic signal. Power signal is also known as periodic signal. So in one sense you can say energy signals are constrained in time, means it cannot go on for infinite time. It will go something like this. What is this mod xt square dt? Isn't this the area under the curve in one way? So if this is the area under the curve, for this to be finite, the curve has to be finite. It has to end somewhere and start somewhere. It cannot go on for infinity. So some finite constraint shape, if the curve signal is of a finite constraint shape, then we have an energy signal. Whereas a power signal is basically a periodic signal. So this is an energy signal, huh? This is an energy signal. So in power signal, what we have is something like this, but this will go on. This is a periodic signal. So what is the energy of this signal? What is the energy of a power signal? We are not yet in the problem, power of an energy signal. We are not yet tackling the problem. We are just getting familiar with the terms power and energy signal. Okay, so what is a power signal? A power signal is something periodic. So what will be the energy? What will be the area under the curve? The energy will be infinite. Okay, now we are going to the problem. So power signal is something which has infinite energy and a finite power, right? How is power defined? Power is defined as 1 by T minus t by 2 to t by 2 xt square dt. So this will be the power. So this thing turns out to be finite. Now we are going to the problem in our hand. What is the problem? The problem is the power of an energy signal. We have derived the energy of a power signal and it's infinity. But what is the power of an energy signal? So what if we want to hello yes, now we want to go to power of an energy signal. So this thing, this pattern never repeats. So what is this power, this pattern is like some t. This pattern never repeats. This is a once, like this pattern only occurs once. So what is the time period? If it never repeats again, can we say that it is expected to repeat again in t equal to infinity? So it never repeats in finite time. So another way of saying a signal is periodic is that its time period is infinity. Time period being infinite and the signal being aperiodic are the same thing. So for this, the time period will be t tends to infinity. So for an energy signal, t tends to infinity. Then p is limit t tends to infinity 1 by t minus t by 2 to t by 2 xt square dt. Here also there will be a mod. Okay, xt square dt. Now t goes to infinite. So what is this? Infinity to minus infinity mod xt square dt. Isn't this the energy? Is it or is it not? This is the energy, right? Energy is minus infinity to infinity. And this is t by 2 to minus t by 2. But the t is itself going to infinity. So this is actually energy. And since xt is an energy signal, what is this quantity? Integration quantity. This is a finite quantity. And what is in the denominator? It's a infinite quantity. So there is a finite quantity on top and there is an infinite quantity in the bottom. There is an infinite quantity in the bottom. So this is finite. E is finite. T tends to infinity. So something finite by infinity, this tends to 0. So power is equal to 0 for an energy signal. Okay? Is this understood? Anyone respond please? Hello? Hello? Anyone please respond? This is an interactive class. You can respond anytime you like. Even if I am teaching, in the middle of my teaching, you can interrupt me. You are free to do that. It's an interactive session. So please interact with me. Just, are you understanding? Hello? Okay. So we will move on to the next problem. Anytime you face any difficulty, you just interrupt me. Energy signal is always of finite duration. So I think we have answered this question already, right? When we defined energy signal, what did we say? That energy signal is something that has to be finite in its length, area. Because energy is basically nothing but the area under the curve, right? Let's go to the energy definition. See, energy is nothing but the area under the curve of xt. If the area is not finite, energy will not be finite. If energy is not finite, it's not an energy signal. So, energy is a signal is an energy signal if and only if the signal has a finite area or finite duration. So, these two are always true. But in some cases, these are always true, but the thing is, if it's finite duration, like if it's a finite duration signal, it will be energy signal. But there is one problem. There are certain cases where a signal, even though infinite in duration, still is an energy signal. Okay, so I said that if the signal is of finite duration, it's energy signal. Like if it's finite, it will be energy. But if it's finite, it will not. If it's infinite, it will not be energy. That you cannot say. Like an infinite signal can also be an energy signal. A finite signal is always an energy signal. But an infinite signal can also be an energy signal under special circumstances. Like if it's a periodic signal, it won't be an energy signal. It will be a power signal. But consider the example e to the power minus t ut. What is the graph? Ut is the step function. So if ut is the step function, means this xt will only exist in the positive half, and it's e to the power minus t, so it's a decaying exponential, nothing fancy. So this is infinite. This is infinite, but this area under the curve, if we do an integration minus infinity to infinity e to the power minus 2t, like e to the power minus t mod whole square dt, so this becomes minus infinity to infinity e to the power minus 2t dt. But there is also a ut. So because there is a ut, the minus infinity to plus infinity part is 0. Minus infinity to 0, I beg your pardon. Minus infinity to 0 part is 0. It does not exist in minus infinity to 0. So it will transform to this integral. 0 to infinity e to the power minus 2t dt. If you remove the ut, the integration limits will change to 0 to infinity. Because ut is such that in minus infinity to 0, it will be 0. What is your definition of ut? Ut equal to 0 if t less than 0, 1 if t greater than 1, 0. So you can simply say that this limit only exists from 0 to infinity. Now 0 to infinity, if you do, this will work out to be 1 by 2. So this has a finite area. The value is immaterial, but it is finite. So the value is immaterial, but it is finite. So even though the signal is infinite, this signal is infinite duration, but the signal has a finite energy, hence it's an finite energy, hence it's an energy signal. So all finite signals are energy signal. Some infinite signals are energy signals. Okay, is the difference understood? All finite signals are energy signals, some infinite signals are energy signals. So the assertion that energy signal is always of finite duration is not true, it's false. Okay? Can you intuitively explain why this, even though the signal is infinite, we can see it's going to infinity, still the area is, still the energy is finite, still this integration is finite? Can you give an intuitive explanation? Like the integration converges, that is a mathematical explanation. Can you give an intuitive explanation? Anyone? Want to try? Just try, just say something. Why does this, even though the signal is infinite, we are getting a finite area, an energy signal? Okay, okay, fine. See, the thing is, if we take this exponential and divide it into small rectangles. In 11-12 you have done area under the curve, right? You used to divide in small rectangles. So you will see that the height of these rectangles, the width is constant, the height of these rectangles are constantly decreasing in an exponential fashion. Okay, so each height is smaller than the next, like bigger than the next height. The next height is smaller, the next height is even smaller. So if one of the height is like e to the power minus 1, then next height will be e to the power minus 2, then e to the power minus 3. So this is a GP, a geometric progression. So but with a decaying common ratio, with a less than 1 common ratio. It's a GP with a common ratio less than 1. And we know from 11-12 mathematics that a GP with common ratio less than 1 converges to a finite sum, to something finite. So we get a finite area. So that's why we get a energy signal. Okay. Okay. Let's go to the next problem. Power signal can be also of finite duration. Now this is straight away false, because power signals, another name is periodic signal. Power signal, periodic signal, same thing. So if your power signal is of finite duration, it cannot be periodic. Periodic means something that goes on and on and on forever. So this power signal cannot be of finite duration. Okay. Achha. Now, if the Fourier series of the signal is given by xt equal to a naught plus this thing plus bn, and the modified xy is given by this, which of the following is true? Okay. Anyone wants to try this one? Okay. Okay, try this one, huh? I am giving you 5 minutes. 5 minutes. Take why 5? Like this is a big problem. Take 10 minutes. So around 6:30, I will knock you at 6:30. Okay? Try till 6:30. Question number 4. Please try question number 4. Okay? Hello. Okay, so is it done? Okay, so let's go to the solution. The Fourier series of the signal. First, we are given the Fourier series in the trigonometric form, and then we are given the Fourier series in its exponential form. So what we will do is we will take the exponential form and we will expand that according to the Euler's formula. Okay, so the exponential form is xt equal to summation Cn exponential minus 2 pi jnt by t. So this is, since this is an exponential, this can be broken down into sine and cos. So what is exponential? Exponential is cos theta plus j sine theta. So this will be Cn cos minus j 2 pi nt by t plus j, sorry, there won't be any j anymore because the j is here, j sine minus 2 pi nt by t. Okay, so we have expanded according to the Euler's formula. So this is summation Cn cos 2 pi nt by t. Since cos is an even function, the negative will just get absorbed, whereas in the sine is an odd function, the negative will come outside. So here we see that it's, now we have got this kind of a relation. Now just by replacing the n with a minus n, replacing n by minus n, we get c of minus n cos and for this one, since if we replace this sine 2 pi nt with sine minus 2 pi nt, the minus will come outside, so this will become plus g summation c minus n. Let me write the summations. So why are we writing two times? Like first we wrote the basic one, then we wrote the inverted one, replacing n by minus n. But why did we do that? Simple, because in the expression for modified exponential Fourier series, you can see that there is a negative infinity to infinity summation. But in the normal Fourier series, there is only a positive summation, n equal to 1 to infinity. So we have to somehow cancel out this negative summation thing. Okay. Now we know that these coefficients for n equal to minus infinity to infinity, these coefficients also have this property, odd even property. So we know that these coefficients will be infinite, like for these coefficients, since these two are same, so like from minus infinity to 0, minus 1, the negative part and the positive part are same, so we can just add them. Whereas in the this part, the negative part and the positive part will cancel out each other. So in the meantime, what we will be left with is an equal to Cn plus C minus n, whereas Bn will be left as Cn minus C minus n, rather minus Cn plus C minus n. So, and we are adding this, so there will be a 2, but since these are all constant, so we can absorb the 2 in that constant. And the answer is Cn plus C minus n, and this will be see, An is Cn plus C minus n and Bn is C minus n minus Cn, means minus Cn plus C minus n, which we have got, minus Cn plus C minus n. And since there is a j here, so this j will also come. Okay, is this understood? Hello? Hello, hello. Please respond. Hello, please respond. Is this understood? Okay, I will assume it's understood. Okay, so moving on to the next problem. So now they say if the Fourier series of a signal is given as the standard trigonometric Fourier series, now they are saying that for any half wave symmetric signal, which of the following quantity is always 0? So an and b2n, a2n and bn, a2n and b2n, okay, or none of these. Which of the quantity is always 0 for half wave symmetric signal? What does half wave symmetric signal means? First we will go to the concept of half wave symmetry. See, we can solve these problems in much in a much faster fashion. We can finish this off, but the thing is, I want to explore the concepts also at the same time while doing the problems, rather than just solving the problems directly. So what is half wave symmetry? First, let me explore what is odd and what is even signal. What do you mean by an even signal? Even signal means for some positive part of the x-axis, if a signal is one way, for the negative part of the x-axis, the signal has to be the same way. This is a this is a even signal. Means for positive part and for negative part, this is t, this is xt. For the positive and negative part, the value is same. So like say, what is the value for 1? T equal to 1 will be the value for t equal to minus 1. They will be same, they have the same value, xt equal to x minus t. And then there is another concept, odd signal, which is that for minus 1 and for 1 the values will be opposite. So for t and for minus t the values will be opposite. xt is equal to negative x minus t. So what is the value at say 1? The value at 1 is 1. And what is the value at minus 1? The value at minus 1 is minus 1. So the value at 1 and the value at minus 1 are opposite of each other. So this is a odd signal. Now we come to the concept of half wave symmetric signal. One second, sorry for the interruption. For half wave symmetric, there will be a T. Sorry. Okay. So in half wave symmetry, what we will do is, there will be a t, time period. This only applies for time periods, like periodic signals. Okay, it cannot apply for random signals. So say we take a signal like this. V. So this V is, here is t by 2 and here is t. Now if we shift this signal half wave, what is a half wave? Half wave means up from 0 to t by 2, half of the wavelength or half of the time period. Okay, so if we shift this signal by t by 2, and this will repeat like this, of course. This is minus t by 2. This is minus t. Like this, this will go on. Now if we shift this by a t by 2 amount, so this thing, let me use another color. This thing, this point here will go to minus t by 2. Okay, so this peak will now be at minus t by 2. So this thing, this zero crossing will now happen here. This peak, so this ending, rather this valley, sorry, not ending, this valley, this was, since this we are shifting by shift by t by 2. Since we are shifting by t by 2, so this peak will go to minus t by 2, and this valley which was at t by 2 earlier will now go to 0. So this whole portion is shifted, and then this portion, this rising portion will go to this thing. Yeah. Uh, hmm. Mm, sorry, let me check 1 second. I may have done a mistake. Sorry, I have done a small mistake. I have labeled this incorrectly. This peak to this valley is T. Then it will be half wave symmetry. So this zero crossing will be at T by 2. Okay. So just rectify this thing. This zero crossing is at minus T by 2 and this peak to valley is T. This peak to valley is T and peak to peak is 2T and this is 3T by 2 and same for the negative side. Now we will shift this signal by T by 2 to observe half wave symmetry. So if we shift by T by 2, this peak which was at 0 will go to T by 2. Wait. Okay, this was a bad example. Sorry, this was a bad example. Uh, let's start afresh. Instead, uh, instead let's take this example. The drawing was not correct, so here we will take a sawtooth waveform. Like this. So this zero crossing will happen at T by 2 and this zero crossing, second zero crossing will happen at T. So zero crossings are happening at half time intervals. Like this. So this is t by 2, this is t. Now let's shift by t by 2. So what was at 0 will now come at t by 2. Yes. See, now what was at 0 will now come at t by 2. So instead of doing like, you can do a left shift or a right shift, whatever you like. Like I am currently doing a right shift. So in the what was at 0 will come at t by 2. What was at like this thing. So this 0 was like from 0 crossing to peak. This was from 0, right? And the next one will come like this. So this will happen at t, and this will happen at t by 2. What was happening at 0? This will happen at t by 2, and this will happen at t. Now from 0 to t, of course, this minus t by 2 thing, this minus t by 2 to 0 portion, this will come between 0 to t by 2 now. So we will have something like this. Sorry. Something like this, and then it will again abruptly jump and it will cross 0 again at t. So this drawing has become a minus t, sorry, this drawing has become a bit like asymmetrical. So what you can see is that at t like this curve is actually the inverted version of this curve. This drawing is a bit bad, but see, the thing is, we are getting this triangle, like this peak at between 0 to t by 2 now, and this valley at t by 2 to t. But instead, and then from t to 3t by 2, we are getting another peak. But now what we are getting is, from t by 2 to t, where there was a valley, we are getting a peak. And from t to 3 by 2, where there was a peak, we are getting a valley. So as if everything has got inverted. So what used to be xt has now become x minus t. So this can be described as xt equal to negative of xt minus t by 2. This is known as half wave symmetry. Okay. So the previous graph was not correct because it was symmetric completely. So that's why I couldn't demonstrate half wave symmetry. So the thing is, this is an honest mistake on my behalf. But this time, this curve, this is not purely odd, not purely even. This is a half wave symmetric curve. You can check yourself. See, the thing is, at t by 2, I am getting this value. At minus t by 2, I am getting this value. Just before minus t by 2, I am getting this value. Just after minus t by 2, I am getting this value. So there is an abrupt discontinuity. So you cannot get an odd or even function from here. What you are getting is a half wave symmetric signal. Okay. So xt equal to x minus of xt minus t by 2. Now we will go to this is the half wave symmetry part I am talking about. Now for Fourier series, we have to find the relation between a and like what Fourier coefficients will always be 0 for a half wave symmetric signal. So for that we will need to find the formula. We will need to get the formula of an and bn. So what is an? An is 2 by t minus t by 2 to t by 2 xt cos omega t n omega t dt. So this is the Fourier coefficient of an. and so an, and then we have also the Fourier coefficient of Bn, but we will not go there now. For A2n, the will minus t by 2, the coefficients are minus t by 2 xt cos 2n omega t dt. Now substitute z equal to t minus t by 2. We will do the half wave transformation because we want to check the properties of Fourier coefficient of a half wave symmetric signal. So now what will happen? This will be 0 to minus t x z plus t by 2, simple substitution, cos 2n omega z plus t by 2. Wherever there is t, I just replaced it with z plus t by 2, and dt and dz will be same, so dz. Now we know, because of the half wave property, rather than t minus t by 2, let's substitute t plus t by 2. It will be more apparent. It's same thing. You can use t minus t by 2 also. So what will be there? This is 0 and this limit will become t. That is more soothing to the eyes. Okay. Z. So wherever there is z plus t by 2, it will be z minus t by 2. Okay, just a minor modification. It's, same either ways, but yeah. So to zx z minus 2. But what did we learn about half wave symmetric? Since xt is, let's write here, since xt is half wave symmetric, what is xt minus t by 2? Nothing but minus xt. So we will just substitute that. Minus xz cos 2n omega z minus, what is omega into t? Omega is nothing but 2 pi by t, right? So what is omega by t? Omega into t. Omega into t is 2 pi. So 2 into 2 pi by 2. So this is actually 2 pi. So 2n omega t by 2 evaluates to 2 pi. So 2 pi n rather, sorry, 2 pi n. Okay. Now let's split the integral. This thing will be cos 2n omega z, huh? So let's split the integral. 0 to t by 2 xz cos 2n omega z dz, and now I'm getting cramped. This part will be t by 2 to t. So I am splitting them into two half waves, right? Now what did we learn about half wave symmetry? That the two half waves are negative of each other, right? The two half waves are negative of each other, and since cos is an even function, so this rather this will also be minus because there is a common minus sign. So minus 2 by t, this thing half wave, minus 2 by t, this thing another half wave. So we learned that these two half waves will be negative of each other. That is half wave symmetry. So this one and this one are negative of each other, and since cos is an even function, this will eventually work out to 0. So a to n will always be 0. Now let's go to b to n. B to n is again now after substituting, I splitted the integral, so it might not be clear. So this time I will split the integral and then I will substitute. It will be more visible how this works out to be 0. Okay. So yeah. Now I will just split it into two parts. Half wave symmetric signal, which is identically similar. I will split this into two parts. Now our main objective here will be to show that these two parts are negative of each other, so that they cancel out and work out to be 0. Let's substitute t minus t by 2 as z. So 2 by t, this will be minus t by 2 to 0, x z plus t by 2 sine 2 on omega z plus t by 2 dt dz plus 2 by t 0 to t by 2 x z plus t by 2 sine 2n omega z plus t by 2 dz. Now the thing is, this integrand of both are same. They are exactly same. So where does these two differ? These two differ in the this part, this limit part. So if we put the limit, actually, like we get the integration and some integration, and we put the limit, then 2n omega z, this 2n omega into minus t by 2. Let's assume this thing works out to be some fz, okay, some integration, some fz. Now when we put 0, the thing is, when we are putting 0, here we have f0, what will be the final result? Say f is the integration, result of the integration. So this will be our result without going into the final result, just the form. So f0 and f0 will cancel, so it is effectively ft by 2 minus ft minus t by 2. Now these things will work out to be minus xt. And this sign when you are putting as 2n omega t, 2n omega, like sine 2n omega t by 2. So this is sine n omega t, and what is omega t? 2 pi. So this is sine 2n pi. And in another case, we will be getting sine minus 2n pi. So these two will cancel out each other, and again we will get a 0. Acha, let's go to the solution. Like I might have confused you regarding the integration. So so what we will do is we will simply substitute, and since there is a half wave symmetry, we will get like, acha, rather than doing for both, actually doing substitution for both actually might be confusing. What you will do is, instead of doing substitution for both, what you can do is you can substitute for one. Hello, any doubt? Hello. So instead of doing this, this might be confusing. So what we will do is we will substitute in only one part. Wait a minute. So we will only substitute in one part. So we will not touch this one. Rather, any one of them, you can substitute in any one of them. So substitute in any one of the integrals, first or second, whatever you like, in first integral. So only in the first integral. So t minus t by 2, this will become from minus t by 2 to 0. The limit will modify. X z plus t by 2 sine 2n omega z plus t by 2 dz. And let's keep the next one intact. Next, this, because of half wave symmetry, this will work out to be minus xz. Sine, now 2n omega t by 2, 2n omega z, sine 2n omega z. Now 2n omega t by 2, I have said again and again, this will work out to 2n pi. So adding 2n pi, like plus 2n pi. So adding 2n pi, like 2 pi to a sine or cos does nothing. So it will just be sine 2n omega z. Now, if we can see this thing, finally we are arriving at something like this. We are arriving at something like this: minus 2 by t, minus t by 2 to 0, xz sine 2n omega z. Now z and t are same thing, na? It's just an definite integral. The variable of a definite integral can be changed. So I change z back to t. Okay, I can do that because it's a definite integral. So I change this back to z. Now, all I have to do is somehow change the limit of the second integral to 0 to minus t by 2. Why? Because then the integrands, the things that are getting integrated are same. See, xt sine 2n omega t, they are same. So the signs are different. This is negative, this is positive. So the only thing we have to now do is change this limit to 0 to minus t by 2. So we will effect a substitution. T is equal to say like z is equal to, or say p is equal to t minus capital T in, substitute, p in second integral. The thing is, you can just directly say these are odd functions, so of course they will cancel out. Okay, don't do this kind of things in competitive exam. If there is a competitive exam, you can always say that this one is an odd function, this one is an even function. So when we substitute, like the signs are odd functions, so when we add them together, it will be something minus the same thing, so it will be 0. So that's how you can easily arrive at the result. But I want to show you the exact theoretical way in which it is like done. So that's why I am doing this. So p equal to capital small t minus capital T. So the first integral will be same. I am not changing anything in the first integral. So I will just copy it again and again. 0. Instead, I will just substitute t equal to t minus t. So now the limit will be 0 to minus t by 2. X p plus t sine 2n omega p plus t. But you see, I said that for half wave symmetry, x has to be periodic. That is like one of the first condition I said. It will neither be odd nor be even, but it has to be periodic. So as xt is half wave symmetric, it must be periodic, right? So if it is periodic, Therefore, x, what will be this xp plus t time period? It is nothing but xp, because t is periodic. And we know that sine is periodic. We know it for a fact. Everyone knows it, that sine is a periodic function. So sine 2n omega p plus t is sine 2n omega p. So finally we get something like this. Minus 2 by t, 0 to minus t by 2, xt sine 2n omega t. Now xp plus t is xp, and this p I am replacing again by t. Why? Because this is a definite integral, so I can do that as many times as I want. So I am again changing the variable. This time p to t, x t sine 2n omega t. Now see, they are exactly the same thing, right? They are exactly same, but this one has a minus in front, this one has a plus in front. So finally you get 0. Is this clear? Is any step not clear? Anyone, please respond. This one is very important, because it is like if you can prove this, then you learn a lot of the techniques that we need to use in Fourier series problems. You will learn most techniques that we need to solve Fourier series problems. Most techniques that we need are there in this one single derivation. Be it substitution, be it splitting, okay, be it using the properties of odd, even, half wave. So understanding this one derivation will help you in all kinds of problems in Fourier series. So is this clear? Please respond na. Okay. Since everybody has left the meeting, so I am hereby concluding the meeting for NPTEL problem solving session. Everyone has left the meeting and no one else is joining. I will wait for 2 minutes, and if no one else joins, then I will be concluding the meeting. Okay, this is Swastik Chakraborty concluding live session 1 for analog communication.